Hi everyone, in this video we'll learn about conditional probability and how to tell if two events are independent. So let's jump right in. So what are random variables? We'll start with defining what we mean by a random variable and setting up the notation for a random variable. Next we'll jump into conditional probability, how we can define it and how we can work with conditional probability. We'll show how to use conditional probability to determine whether or not two events are unrelated or independent. And then finally, we'll talk about the multiplication rule, which is a really handy shortcut tool we can use if events are independent. So let's start with random variables. So a random variable is a variable which takes on numerical values. So we'll assign each of the outcomes of a random experiment to some numerical value, each with a corresponding probability. These random variables can be discrete or continuous. We'll continue to focus on the discrete case for now. Notationally, we'll use capital letters like capital X, capital Y to indicate random variables, and lowercase letters like little x, little y to indicate the observed values of those random variables. So let's start with the definition of conditional probability. So the idea with conditional probability is that we are limiting our sample space or focusing on just a smaller set of outcomes. So we say that the conditional probability of A, or the probability of A given B, indicated with a vertical bar, is the probability of A and B divided by the probability of B. Now, as long as there is some probability associated with B, so the probability of B is greater than 0, this definition works. So essentially what we mean by conditional is that we are limiting ourselves only to the set of outcomes in which B has already occurred. So given that we know that we fall into B, so to speak, what is the probability that we also fall into outcome A? As a simple example, take a balanced six-sided die. Let's find the probability of 1 given that an odd number has occurred. So, unconditionally, the probability of rolling a 1 is 1 out of 6. There are 1 sides of the die with 1 out of 6 total. However, if we want to condition or restrict ourselves to the event that an odd number has occurred, there are now only 3 possible outcomes in the sample space, a 1, a 2, a 3, only one of which is a 1. So that's how we go from 1/6 to 1/3. Let's take a look at a different example. So suppose that you're choosing to watch some movie with your young nephew. Your nephew loves watching movies on Netflix, specifically ones about puppets. However, you've also been given an instruction that your nephew should only be watching G-rated movies. There are 1,284 movies that are available to you on Netflix Kids, 272 of which are G-rated. Your nephew likes movies with puppets, which turns out to make up 94 of the G-rated movies. There are only 30 movies with puppets that are not G-rated. So let's say you are scrolling through Netflix looking at the preview images and your nephew sees a movie with puppets and that's what he wants to watch. What's the probability that it's also G-rated? Well, we know that 94 movies with puppets are G-rated. We also know that 30 movies with puppets are not G-rated. That means that in total 124 movies have puppets. So to find the conditional probability that a movie with puppets, or given a movie has puppets, it's also G-rated, we'll take the number with puppets, 124, divided by the number with puppets and G-rated, 94, we get about a 76% chance. It does get more complex than this, however, this is a good example to illustrate sort of how we build out a sample space with a condition. Okay, so let's talk a little bit now about independence and relationships between two random events. So suppose that the probability of A and B are unrelated. A occurring does not affect whether B occurs, B occurring does not affect whether A occurs. If this is true, we say that events A and B are independent. Now we can use conditional probability as a check for independence. So for example, if two events A and B are independent, then the conditional probability of A given B should be equal to the probability of A. That conditioning has not affected the probability that A occurs. Similarly, the probability of B given A should be the same as the probability of B. From these two properties, we can work our way to a third with just a little bit of algebra. And the third property looks like this. The probability of A and B under independence must be the probability of A times the probability of B. So let's take a look at an example. We have two events, A and B, such that the probability of A is 0.5, the probability of B is 0.3, and the probability of A and B is 0.1. We'd like to find the conditional probability of A given B, and then use that to decide whether these events are independent. So let's start with the conditional probability. The probability of A given B is the probability of A and B divided by the probability of B. So we take 0.1 divided by 0.3, we get 33% or 0.33. Looking back to the previous slide, the probability of A was 0.5. So if these two events are independent, then the conditioning shouldn't matter. However, it seems like it does. The probability of A given B, or 1/3, is not the same as the probability of A. So A and B are not independent. Now, from independence, we can get to the multiplication rule, which is an incredibly useful tool for finding probabilities of independent events occurring simultaneously. So let's say that we have two independent events, A and B. The probability that both occur, the probability of A intersect B, is the probability of A times the probability of B. This extends, so if we have a third event, a fourth event, a fifth event, we just continue to multiply. So, as you can imagine, finding probabilities of multiple events occurring at once, incredibly useful with this rule. So, let's consider 3 random days in the semester. On Mondays, you wake up 45 minutes before class. The probability that you get to class on time is about 98%, so Mondays are pretty good days. Tuesdays, a little bit more rushed. You wake up 30 minutes before class, you've got a 71% chance of being on time. Wednesdays are rough. You wake up 5 minutes before class, you only have a 16% chance of being on time. So we'd like to find the probability of some events. We want to know the probability that you're on time all 3 days, the probability that you're late all 3 days, and then the probability that you're on time, at least once in the week. So I'm going to let OT represent the event that we're on time. Each day of the week will be denoted with a capital letter, Monday M, Tuesday T, W, Wednesday. L will represent the probability that you are late. Now, on time and late will assume to be complements. You can either be on time or you can be late. So let's find the probability that you are on time to class all 3 days. Now, each day, the probability of being on time is a conditional event. It changes depending on the day of the week. However, we can still use the multiplication rule even though these are conditional events because they're independent from each other. The days themselves are independent. So we have the probability that we're on time on Monday times the probability that we're on time on Tuesday times the probability that we're on time on Wednesday, which works out to be about 0.11 or 11%. Now for the probability that we're late all 3 days, we're going to take the multiplication rule and combine it with a previous one, the complement rule. So the probability that we are late is 1 minus the probability that we're on time. So we get 1 minus 0.98 times 1 minus 0.71 times 1 minus 0.16, and we get about a 0.5% chance of being late all 3 days. So we're probably not going to be late all 3 of the days. To find the probability that we're going to be on time at least once, we'll use the complement rule again. So the probability that we're on time at least once should be 1 minus the probability that we're late all 3 days, because we're either late all 3 of the days or we're on time at least one of them. So there's a 99.9% chance, or 99.5% probability that we'll make it to class on time at least one of the days. Let's take a look at one more example, again combining the complement rule with the multiplication rule. So we have 10 students who are going to order noodles at a local restaurant. Each student is known to prefer Japanese pan noodles 40% of the time. Those are the most popular menu item at this restaurant. We'd like to know the probability that all 10 students order the Japanese noodles, that none order the Japanese noodles, and that at least one orders it. So let's start with all 10. I'm going to let P of n be the probability of ordering Japanese noodles. For each individual student, it's only 40%. We'll make an assumption here, and our assumption is that the students are choosing independently. They didn't come in a group, they're not talking to each other about what they're going to order, they're all just making their order without consideration for what the other students are ordering. So the probability that all 10 order the Japanese noodles is the probability of ordering the noodles once raised to the 10th power, or about 0.0001. To find the probability that none of the students order the Japanese noodles, we'll use the complement rule and the multiplication rule together. So first we need the probability that a student does not order the noodles, which is 1 minus 0.4. Those are all independent events, so we'll raise that to the 10th power. We get 0.006 for that answer. Then finally, what's the probability that at least one of the students orders the Japanese noodles? Probability of at least one is the complement of none, so 1 minus, we get 0.993. So in the next video, we'll talk a little bit more about conditional probability and how to find conditional probabilities in more complex situations using Bayes' rule.